Okay, hey folks, picking up here right where I left off. So I've got the learning goals here in front of me. Oh, great timing that I had to sneeze right when I started the video. That's okay. I'm not stopping. I'm going to keep going. So I just covered a couple of those first learning goals, just taking it a few at a time here. So understand the property of light waves, frequency, wavelength, amplitude, interference, refraction, as well as be able to perform calculations using the equation. Okay, and so we'll get a lot of practice of this in the discussion. And be familiar with the electromagnetic spectrum and know the wavelengths, approximate wavelengths for UV, visible, and IR. Okay, so visible we know was 400 to 800, and so knowing the wavelengths for ultraviolet and infrared, just understand that UV are smaller wavelengths than visible, so smaller than 400 nanometers, and IR are wavelengths bigger than visible light, so bigger than about 800 nanometers. Okay, and on this next video, I'm just going to go through two more. Understand the photoelectric effect and be familiar with the dual nature of light. So we're going to talk about these two learning goals in this video. Okay, so the photoelectric effect is a result, one of the results of quantum mechanics. Okay, and as it turns out, this was Einstein's 1921 Nobel Prize. So this is some pretty cool stuff. So the way this works is when you shine light, and in this case, this is specific to a metal in vacuum. So you have to imagine, let's say this whole thing is inside a vacuum chamber. And the reason for that is so that you don't get interferences with the surrounding gases. Okay, gases can actually absorb some of the light that would be used in this experiment, or even can be ionized by these electrons. So this is all in a vacuum. Okay, and as it turns out, if you shine energetic enough light on a metal in vacuum, it will photoionize. Photoionize. So in other words, it'll eject an electron as a result of energetic light coming in and knocking that electron out. Okay? And so this picture shows you two cases. One in which a red photon at 700 nanometers is used, and one in which a UV photon at 200 nanometers is used. And if our metal were potassium, we would not observe anything happening when red light is being shined on this metal. We would not observe any ionization or photoelectrons. But if we used a 200 nanometer photon, this would be energetic enough to knock out that electron. Okay? And so from this idea, Einstein came up with this equation. The kinetic energy of the electron that is ejected, so kinetic energy, because if you think about it now, this electron is in motion. So it's the energy that it has when it gets ejected is kinetic. The energy that it has when it's sitting in that metal is its potential. Okay, and so this all equals h times nu, and we remember that h times nu is energy, and this is specifically energy of the photon, and I'll write another note that says that's the incident photon. So here is my incident photon. So that means the photon that's being used to drive this reaction, which is expressed right here, right? Potassium metal plus H nu. So we often use H nu to abbreviate photon or light. So we can use that in a chemical reaction by saying K plus light makes K plus plus an electron. It ejects an electron. Okay? So now the kinetic energy of this ejected electron will equal the energy of the incident photon h nu minus what we call the work function. And that's just a fancy way of saying the energy required to remove the electron, okay? And so we could say phi equals also h times nu sub 0. We could also say phi equals hc over lambda. We could also say phi equals this energy that I have right here. So phi, this work function or energy required to move the electron, can also be related to this number. So for potassium, 1 mole of potassium requires 419 kilojoules of energy to remove 1 mole of electrons. So here's what we have to remember. This is where this is going to be the hardest for our calculations. All of these h nu or hc over lambda calculations are for one single electron, not for 1 mole of electrons. However, this energy, this work function energy, if it's given to us as 419 kilojoule per mole, we have to convert it into joule per single atom. So we have to do that conversion to make this calculation possible, okay? So let's do that. Let's do this calculation here. So calculate the kinetic energy of the ejected electron in the picture above. So this picture, and what this is really referring to is not this one, because we know this one didn't result in photoelectron, but it's referring to this picture right here where we use a 200 nanometer photon, and we know that potassium metal has a work function of 419 kilojoules per mole. Well, as I said, the first thing that I need to do is convert that to joules per single thing, okay? So I know that 1 kilojoule is 1,000 joules, and I know that 1 mole is 6.022 times 10 to the 23, and I'm just going to leave it like that. I don't have to technically put in atoms or molecules or things, because it's implied that that's just going to be a singular thing that we're talking about, okay? So 419 times 1,000 equals, and then now divided by 6.022 e to the 23 equals, and that looks right, okay? So 1, 2, 3 sig figs, because I had 419, so we'll say 6.96 times 10 to the minus 19 joules equals phi. So I remember that my equation is kinetic energy of the electron equals h nu minus phi. So now I have to calculate this quantity h nu, but I don't have the frequency in this picture. I have the wavelength. So I recognize that h nu also equals hc over lambda. So in this equation, I can also say that hc minus lambda minus phi also equals kinetic energy. Either one of those is okay, depending on what, if I have the frequency or if I have the wavelength. In this case, I have the wavelength, okay? So let's do that calculation. So we know h is 6.626 times 10 minus 34 joule times seconds. We know C is 2.998 times 10 to the 8 meters per second. And here this wavelength, 200 nanometers, I'll put this down here in the notes, or in the side. So I know 1 nanometer is 1 times 10 to the minus 9 meters. So automatically I know that's 2.000 times 10 to the minus 7 meters. Okay, be quick with those unit conversions, all right? So now that's divided by 2.000 times 10 to the minus 7 meters, which is the same as my 200 nanometers, okay? And so when I do all of this calculation, I get, let's see, 6.6626 E. So on my calculator, I have to say 34 and then minus. Maybe that's what you have to do on your calculator as well. So times 2.998 E8 equals, and then divided by 2E7 minus equals, okay, good, that looks right. 9, and then now I have 4 sig figs here because of 200.0. So that's 9.932 times 10 to the minus 19 joules, okay? And now finally, I can say the kinetic energy of the electron is going to be this quantity minus that quantity, okay? 9.932 times 10 minus 19 joules minus 6.96 times 10 minus 19 joules. Okay, and so I'll leave this in the calculator here, and I'm just going to say minus 6.96 E19 minus, and yep, I get, and then 3 sig figs now because of my work function. So that's going to be 2.97 times 10 to the minus 19 joules would be the kinetic energy of that ejected electron. And it's a tiny number because it's one single electron we're talking about, right? And so just like we did in that previous example, going back here, I'll show you, where did it go? Maybe I passed it already. This example, right? Where we can take our energy of one photon and we can multiply it by a mole, and that gives me the energy of a mole of photons. So realistically, you're not going to be shining one singular photon on one singular potassium atom and knock out one single electron. However, these calculations are easiest done under that assumption that it's one single thing. But now we recognize if, let's suppose I had a mole of potassium or had 5.62 grams or whatever, I can use this number just like my other dimensional analysis numbers and scale that number up if I had more than just one single electron being ejected, okay? So now, calculate the minimum wavelength of light needed to ionize potassium. So it says we're going to do this in the discussion worksheet, and we will. I'll do another example. I'll give you a different example than this one. But now if we think about it here, okay, the minimum wavelength of light needed to photoionize, if we think about this, is going to be, so I'm going to write this as hc over lambda minus phi. The bare minimum energy will be when the kinetic energy is 0, because now anything that's slightly more energetic than this number, so the energy that satisfies this equation, now that this all equals 0, that will represent the bare minimum. Okay, hopefully that makes sense. And so now what I get from that, what I can see if I wanted to rearrange this, I could say now, doing the algebra here, phi equals hc over lambda. And I'm going to keep doing the algebra because they asked me for the wavelength, the minimum wavelength, right? And so rearranging now, that's going to be lambda equals hc over phi. Okay, so it's as simple as that. So now I can say that minimum wavelength I need is going to be 6.626 times 10 minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second. And then now I have to use my singular value of phi, right? Which was the 6.96 times 10 to the minus 19 joules. Okay, so let's see when we do all of that. So 6.626 E minus 34 times 2.998 E8. Okay, and then now divided by 6.96 E19 minus equals, okay, cool. And that gives me so we'll just say 3 sig figs, 2.85 times 10 to the minus 7, and let's check out the units. So seconds and seconds cancels, joules and joules cancels, and now that's units of meters. So it didn't say to what unit to convert it to, but when in doubt, converting to nanometers is always a good thing, so we can see what region of the spectrum that we're in. So I know 1 meter is 1 times 10 to the positive 9 nanometers. And now this is going to allow me to just do exponent math, right? So minus 7 and positive 9 gives me positive 2. So that's 2.85 times 10 to the positive 2 nanometers. That's the same as 285 nanometers. And that makes good sense because look, when we used a 200 nanometer photon, which remember, 200 nanometers is more energetic than 285. I know the number is smaller, but we have to remember because it's a small wavelength, it's a big energy. Okay, so this 285 is just slightly bigger in wavelength, which means it's just slightly less than energy than 200, and that makes good sense that this 285 nanometer represents a minimum. So if I shined 286 nanometer light on potassium metal, it would not photoionize it. If I shined 285, it would still not ionize it because the kinetic energy is 0. However, if I used 284.9, right, then I would get photoionization. I would get an ejected electron. Okay, so why is this important to know? Well, as it turns out, this photoelectric effect is widely exploited in modern electronics. Okay? So here's an example of a photomultiplier tube, and this is pretty old school photomultiplier tubes, but all the same, we wouldn't have the technology of today if we hadn't had these photomultiplier tubes. These are largely used in older electronics. You might just hear these referred to as a phototube or even just a tube. Like I still love my guitar amp that's a tube amp. Maybe you guitar heads out there know about tube amps. Those are photomultiplier tubes, okay? And so the idea of these things is you can induce a current through light. So here is the tube, the phototube itself. It's an actual tube, right? And inside of it is a vacuum. Okay, so it's evacuated. And here what you have is this positive electrode. So that's the electron collector. And so what ends up happening when light of a very specific frequency or energy, right, it has to be slightly above the minimum energy of whatever the metal is, right? So now when light hits that surface, an electron gets ejected into this collector electrode and it completes the circuit. Okay, so now you've got electrons that flow and that can flow into this device and out the other device, which is pretty cool. So these are widely used as light detectors. So that's really what this is. This example is showing you this as detecting light because you can see it's got a voltage source already. And so I've got an example of one of these things. It's the remote control to my stereo, right? It uses infrared light, and when I point it at the stereo, it completes a circuit from the signal via this photoelectric effect, and that's why I can use that thing. Okay. Some of them also use radio waves, but more often than not, your remote controls use infrared. Okay. And also based on the same principle, if we take the battery source away, okay, and we talk about a solar panel, right? Then largely it's not quite the same as the photoelectric effect, but it's a very similar idea where light is being shined. And now an electron is not ejected into vacuum, but rather an electron gets ejected into some wire. So a wire collects those electrons and can be used for power. So that's pretty cool stuff. Okay. So let's see here. What's the next subject? So the last thing I want to talk about here, getting into more of these properties of light. And this is a really cool one, the dual nature of light. So this is something that has been mind-boggling for physicists and chemists alike for 100 years. So light, as it turns out, is a particle and a wave. Simultaneously, it can exist as a particle and a wave. And there's really good examples of both. So here's the famous Young's double slit experiment. And I'm going to show you a video of this soon. But the way the double slit experiment works is from the following. So we shine a beam of light. So this is showing you light as a photon. So whenever you see like a little particle, you know, we think of it as a photon. However, in Young's double slit experiment, he demonstrated that that photon really acts like a wave. Okay. So as it passes through a slit, which is just a narrow opening, light does what's called diffraction. So we talked about refraction, but now this principle of light spreading out as it goes through a narrow opening is called diffraction. And so if what you would observe here is, so suppose we have a beam of light coming through so we can see it diffracting. If we just had one slit opened, we would just observe a whole like beam of light, like a whole spread out mess of light, okay? And so this is showing you if you have like, you know, the right slit open, you get this thing. If you have the left slit open, you get the same thing. But now if both slits are open simultaneously, then you start to see the manifestation of light as a wave. In other words, what happens is it interferes with itself. Just like I showed you, let's back all the way up, just like I showed you in this slide. When the light is now forced to pass through two openings, you can get constructive and destructive, simultaneous constructive and destructive interference, where you have really bright spots and a bright spot, and let's say no spots at all, okay? So I'm going to show you, instead of these like pictures here, I'm going to show you an actual video of this. This is from the YouTubes, so this is pretty cool. So let's watch this.
For you to do this experiment in pairs. So what does it involve? It involves this, which is a spirit level that's got a laser in it. So if I point that at the wall there, hopefully you can see it's a red laser. It's a nice low power laser that's going to be safe for us to use. Young did this hundreds of years ago, so he didn't have lasers, but they make our life easier, as you will see. We've got this thing here, which is a collection of double slits. So if you look really closely, you can probably see 4 slits in this slide. If I hold it up to maybe a white background, you see more clearly. Each of those things that you can see there, oh no, that's lovely, that's focused really nicely. So you can see that each of those things that look like one slit is actually a pair of slits. And the ones on the right are quite far apart, and the ones on the left are really close together. So these are double slits. What happens when the light passes through these two slits is that it spreads out. So when light passes through a narrow gap, it spreads out, it diffracts. And then the light coming from each of
Diffraction.
those slits can interfere. So I'm going to shine the laser light through. I'm going to use the leftmost pair of slits because that's going to work best. So I'm going to shine this laser through a double slit, and then all the way over there, I'm not sure if you can see it, is a screen. It's a long way away, and you'll find out why that is shortly. So, here we go. I'm going to turn the lights off.
I think this guy's like a high school physics teacher in England.
And I'm going to direct the laser through 2 of the slits. So the laser light is going through a double slit, 2 slits very close to each other. All the way down there on the screen, you might just see some red. Now, actually, let me show you what it looks like without the double slit. Without the double slit, it looks like a dot.
Just a beam, a bright spot of light,
Okay.
which is kind of what this picture is showing you here.
Now, put a double slit in the way. So the laser light is passing through both of those slits. It's spreading out, it's diffracting. But when it gets over here,
Look at that. That's awesome. There is the interference pattern, right? So you can see where it's really bright, that's where there's maximum constructive interference. And where it's really dark, those dark spots in between are the destructive interference, which is also really cool. So I'm going to put that away now here. So that's light acting as a wave. But what about light acting as a particle? Well, once again, kind of reiterating, showing you what that Young's double slit experiment showed you. If we're thinking of light as a photon, so photon is like a particle, okay? Like a little ball, like a little billiard ball that can fly off ballistically, okay? So what you would expect, this is what you would expect if light is a particle. All of those particles would just funnel through those two narrow slits, right? And you'd see like a whole bunch happening here and a whole bunch happening there, okay? But that doesn't really explain what's actually going on. What's actually going on is that they're interfering with each other, okay? So a really good example of light acting as a particle is through a laser light show, believe it or not, okay? So you see all of these lasers here, and we can see a nice straight beam trajectory. I mean, have you ever wondered why you don't observe this with your laser pointer? Like, I don't have a laser pointer right now, but if I shot a laser pointer, I can see it reflecting off of the surface wherever it's pointed, but I can't see the actual laser line. So what they do in these laser light shows is they put a bunch of aerosols or particles or like smoke right in the air. And so now you have all of these smoke particles in the air, okay, which I'll draw as dots, all right? Okay. And as a beam of light comes through, let's change my color. So now let's say here is my photons, and I'm just going to draw them as one single line. Like suppose I've got like a laser pointer, you know, shooting my photons out, okay? So they're all coming out ballistically, and now when one of those hits one of those particles, it goes scattering off that way. And when another hits another one of these particles, it goes scattering off this way. And so now all of these photons, this probably looks like a mess, right? But all of these photons are scattering off in all directions. They're all being spread out in every direction. And now for you, random person in the audience here at this laser light show, you're going to see that beam being scattered off one of those smoke particles that's in the air, okay? So this is not an interference thing. This is just a one particle colliding with another particle and going off in another direction, all right? Which is pretty cool stuff. So again, the dual nature of light, light acts like a wave, but it's also like a particle. So that photoelectric effect idea that I showed you, that's kind of light acting like a particle. The Young's double slit experiment and these interference patterns, that's light acting as a wave. Laser light shows where you actually see that beam of light because it's being scattered off of some like smoke particle or some aerosol, that's light acting as a particle. So we kind of have to accept that the current state of physics on light is that it's both. It's both a wave and a particle. And that's a pretty good place to stop, folks. So I'll pick up on the hydrogen spectrum and the Bohr model in the next lecture. All right, hasta.